Episode 113, White Dwarf Destiny. And welcome back to another edition of the Syzygy podcast. My name is Chris Stewart. I'm in the office of one Dr. Emily Brunsden. There may be more, but I'm with one of them. Emily, how you doing?
I'm very good, thank you.
Good. It's been a little while.
Yeah.
It's like longer than we expected.
No.
I think after every episode, we always know that there's going to be a gap of, might be a week, might be a couple of weeks. But this time around, you were busy, I was busy, I went away, I got sick, you got sick. And here we are. It's nice to be back. And today's a very exciting one because this is one of those times where, we say at the end of every episode, hey, here's how you can get in touch with us, and send through your questions or suggestions for what we might do an episode on. And we had one, someone got in touch, one of our very early listeners. She said she's been listening from episode 1.
Whoa.
So we were contacted by listener Sophia Sechesna. I hope I've got that right. I've tried really, really hard on that one. So if I haven't got it quite right, do contact us again and say, no, it's pronounced this way. But you did challenge us in the email, Sophia. So, I gave it my best shot. Point is, contacted us through the website and said, hi, I've been listening for a really long time and I'd really love you to do an episode on white dwarf stars because Sophia is she has a PhD, or she's doing a PhD, it wasn't quite clear, in sort of the boundaries of art and science. And so she said, my next project is on white dwarf stars. Could you do something? And so I said to Emily, could you do something? And she said, absolutely. So that's what we're doing today. Emily, we're doing your top 3 interesting things about white dwarfs.
So obviously if you just give a topic kind of it's as big as white dwarfs, we couldn't cover even 5% of what is interesting, I think, about white dwarfs in a single episode.
Yeah, there's a lot there.
There's huge amounts, right? So what I thought I'd do is kind of just pick out 3 of my favorite things about white dwarfs. And I'm trying not to go into the song here because I've titled this episode, at least in my notebook, of a few of my favorite white dwarf things.
Ah, right. I was wondering what the song was. Was there a white dwarf song that I wasn't aware of? No, that one. Okay.
Yeah.
Good.
Anyway, so these are 3 of my favorite things.
About white dwarfs.
Excellent.
But before we get there, we've got a little update. Emily, what's been going on?
Yeah, so I saw a couple of things. Well, actually, the most interesting for us is OSIRIS-REx.
Yes.
You'll remember that we had the big media announcement that wasn't delayed by various political situations, which is good. Opened up, had a look, managed to get, I think they've up to about 70 grams of stuff, which is just from the outer container.
So just remind, backing up, for people who maybe didn't listen or have forgotten, what was the big news about OSIRIS-REx?
Oh, yeah, we should probably go back to that.
Yeah.
So
Quick recap.
OSIRIS-REx went to an asteroid, picked up some stuff, came back, returned to Earth, and we've now got
sample return mission. We've got stuff, the most stuff we've ever had.
Yeah.
To look at from an asteroid, a special kind of asteroid, wasn't it? Was it or not?
Consult episode. my brain's it's gone.
Anyway, we've got all of this stuff. It's come back from outer space, and if I remember correctly, the scientists got a first look. It was like opening that first Christmas present on Christmas morning. And then they were going to sort of distribute stuff off across to researchers across the planet. So what's happened? Have we had an update?
Yeah, so they were expecting to get about 60 grams total from this. So there's kind of 2 containers. There's the outer container, which might get a tiny little bit contaminated, but it's kind of okay. And then there's the inner, really preciously sealed.
The inner sanctum, yes. Don't breach this unless you really know what you're doing.
Yeah. So the outer one was the first look kind of date source, and they got 70 grams of stuff just from that.
Right.
When they're expecting 60 for the total.
Wow.
So that's cool.
Pay dirt, quite literally. Yeah.
Yeah, loads of it. So they're quite happy with that. Problem is they're having a little bit of trouble getting into the inner sort of sealed unit.
Trouble getting into it.
Yeah.
But they built it. What's the problem here?
Well, the very brief article that I saw says that they've got 35 kind of screws, sort of, I don't know, holding together mechanisms.
Yep.
And 2 of them are a bit jammed and they don't have the correct tools in the glove box to open it. Now we say glove box, not as in the glove box in your car, but glove box as in this is a temperature, pressure controlled environment box where you've got some gloves so that you can stick your hands in.
Yeah, they look quite crazy. There's some here in the physics department in various of the labs you wander past, and you just sort of see these large, metallic units with a window on the front, and then sticking out of the window are these large sort of arm-length rubber gloves, which, because they've been pulled out of the unit, are now just sort of sticking up like arms into the air, which is quite bizarre. But that's what we mean by a glove box. And so inside there, in the special unit, they haven't got the right tools to break into the box.
That seems to be the gist of it. They don't have the right screw head.
Rats. That's a bit embarrassing, but I'm sure they'll figure it out.
Yeah. So
Okay.
we just have to wait a little bit more on that one.
All right. Well, thank you for the update, and good luck to everyone who's working on that problem. I'm sure this isn't beyond the wit of all of the researchers involved. So, good luck, and I look forward to the next update. Yeah, but back to the topic du jour, which is, by request, white dwarf stars. So, Emily, shall we begin with what is a white dwarf? What is a white dwarf star? That seems like a suitable place to start.
Yeah. So a white dwarf is a remnant of a star when it's gone through its life cycle. And specifically, it's the remnant of a star that has a mass up to 10 times the mass of the sun.
Right. Okay. And I know that the sun is a fairly common or garden variety kind of star. And so these are common?
Yes,
there's lots of these things up to 10 times the size.
Yeah,
of the sun.
so in terms of stars that are going through the normal parts of their lives, so up to 10 times the mass of the sun, you're talking about up to around about 97% of stars in the Milky Way have that mass.
Right. Okay. So that's a lot. And then there's a long tail of ever larger stars, but there's not many of them.
Not many.
Right. Okay.
Yeah.
Okay.
So most stars in the Milky Way will become white dwarf stars, but they've got to go through some kind of transformational process to get there. Mm-hmm. So we talk about stars going through the normal part of their lives, like the sun is when they're fusing hydrogen to helium. That kind of runs out eventually, and we go through several steps of what we call main sequence evolution. There is a nice syzygy episode where we talk about all this in much more detail. So I'm giving this the very briefest overview.
I'll have to go and remind myself of which episode number that is, but it'll be in your show notes. Just go and check the website.
So we've got main part of the life cycle doing hydrogen helium fusion, red gianty stuff. And at the end of the red gianty stuff, then the star is shedding off huge amounts of its outer layers. So it's puffed up to this enormous red giant. It can't hold on to all that mass.
And we are talking enormous here. Like these things are huge.
Yeah, red giants are massive.
Yeah, like out to sort of the Earth's orbit kind of thing.
Yeah.
Wow.
So massive stars, they can't hold on to it all. So they just sort of puff it off. And eventually you're left with just the compact core, which is the remnant of what used to be the bit that was sort of fusing hydrogen to helium. That's all been used up. So most stars will end up with a carbon-oxygen core that becomes the white dwarf star as its own entity.
Right. So this isn't post sort of supernova or anything like that. There hasn't been a massive explosion. There's been puffing up to this sort of pufferfish style, huge red giant thing. And then just gradually losing all its outer layers, or does that happen fairly quickly?
Well, it depends on your view of quickly. In a few million years.
Yeah. Is that quick on astronomical
It's pretty
scales?
quick.
It's pretty quick. Yeah.
These last few puffs anyway will be in the last few million years of the life. Yeah.
Right. And this is the sun's destiny. Yeah. The sun will become a white dwarf eventually.
It will, yeah.
Cool.
So when you talk about a white dwarf, it's actually a really hot, compact star. So to give you an idea of the temperatures, we're looking at, tens of thousands of Kelvin, degrees Celsius, when they kind of emerge from the puffed out atmospheres.
As opposed to the sun, which has a surface temperature of several
5,800 Kelvin, so 6,000 roughly, more or less. And they're really, very compact. So they've got the mass of the sun crushed down to the size of the volume of the Earth.
Wow.
Yeah.
That's quite compact.
They're really compact because of all the pressures that have gone on during the star's late part of their lifetimes. It's kind of crushed this core together, really, really compact.
Wow.
So basically it's 1 million times smaller than the sun to go from the sun to the Earth. To crush it down, you've got to go a million times.
A million times smaller, but same mass.
But same mass.
So that's incredibly dense.
Incredibly dense.
Now, we haven't reached crazy matter phase. Like, we haven't gone to neutron star, which is where you don't really have atoms anymore. You've just got, it's almost like one giant nucleus in a neutron star, which is weird. We haven't got to that point. It's still kind of normal matter.
Sort of normal, but not really. It's
what
not,
is normal?
Let's be honest, it's not really that normal, because once you've done this, so imagine if you've got a bit of white dwarf, right?
Yeah.
The density is so much. If you've got a cubic centimetre, so a cube that's a centimetre on each side, that's going to weigh a ton.
Wow. Okay. Yeah. I mean, dense.
Yeah.
You already knew that.
Really, really dense. So normal matter doesn't do it like that, right?
No.
You can't just sort of take a bit of whatever, your coffee, and crunch it down until you get something, amount of coffee that fits inside a ton of coffee into a centimetre cubed. It doesn't work.
That's where we can't do that.
No. So what this matter is, it's degenerate matter. So what that means is they still kind of exist as then a kind of atom identity. So you have a nucleus, for example, mostly carbon and oxygen in these stars. So you have a carbon nucleus, or many, many carbon nuclei swimming around, but they're swimming around dissociated to the electrons.
Right.
So it's kind of a soup where you've got the nuclei of your elements and your electrons swimming around, but they're not in an atom bound to each other in that way.
Right. Because what you typically have in normal matter is, like, sure, imagine a carbon nucleus, maybe 6 protons, 6 neutrons bunged together into the tiny nucleus. But that's just one tiny little dot at the center of a much larger atom, which is all of the electrons in sort of clouds around the outside. But the nucleus is tiny in comparison to the entire atom. And it's those, if you imagine that as sort of a sphere, it's those spheres which are, I'm waving hands here enormously from a physics point of view, but you imagine those spheres as big beach balls sort of bumping up against each other, and they can stick to each other and make solids, or slide past each other to make liquids, or float freely with each other to make gases. But that's the size scale. I'm interpreting what you're saying and saying, like, get rid of the beach ball part, and you've only got the tiny little walnut nucleus at the middle, and all of those are now running around bashing against each other.
Yeah.
And that's why you're able to get this incredible density, is you haven't got these huge, by comparison, electron clouds getting in the way.
Yeah.
You've now just got nuclei bumping into each other.
Yeah, the electrons
Wow.
are still there. They're just kind
Yeah.
of free to move in what would have been the space, the empty space
Right,
of the
right.
atom before.
Right. So we're very much into crazy nuclear plasma kind of territory.
Yeah. So it's a plasma, and we call that the state, or at least the pressure that's now holding up this star, because it's not fusing anymore. There's no fusion. There's no energy output.
Oh, so none at all.
None
Okay,
at all. It's
right.
all gone, right? There's nothing left. So the whole thing that's holding up the mass of the star is what we call electron degeneracy pressure. So the whole object is degenerate. It's squished down to its smallest possible configuration that quantum mechanics will possibly allow before everything just breaks, basically.
Yeah.
The nuclei start to break.
It's one of the crazy things about quantum mechanics that there's rules about what the particles are allowed to do. And some particles are allowed, you can fit as many of them as you want within limits, within a certain space. Photons of light, you can just squeeze loads and loads and loads of those into the same place, if you like. But electrons, you can't.
No.
There are rules about how many electrons you can have in what we call in physics the same state, which we can think of here as squeezed together into the same place. And in fact, you can only have one. You can't put two, let alone an entire star's worth, into a really small area. And so there's a limit to which, there's a volume limit to which you can squeeze those particles down to before physics says, nah, can't do this anymore, which is kind of nuts, really.
It's crazy.
But as we mentioned before, there are, as stars begin to collide, they're always trying to collapse under gravity, right? And so it always comes down to, so what stops them collapsing down towards their core? And for a star like the sun, it's what? The radiation?
Yeah,
the outwards radiation pressure?
Yeah, the photons, the fusion that's going on inside.
Right. That's all
the
pushing
core.
out.
Yep.
Gravity's pulling in, and you find that balance. You run out of all of that outwards radiation pressure, and it collapses down until you reach the next limit. And in this case, the next one is this electron degeneracy, where quantum physics says, go no further. So that's kind of cool.
It's very cool.
Yeah.
It's very, very cool.
So you said that they're really hot, but they're not fusing anymore. So is the heat, is that energy just left over from that collapse?
Yeah, what's left, it's not so much it's partially the collapse, but it's also just what the temperature of the core of the star used to be, right?
Right.
So the core of the sun's a few million degrees, Kelvin, Celsius, whatever. Cores of stars are very hot, basically. So if you just take off the atmosphere and had a look, still very hot. It takes a long time to cool.
Right.
So yes, you have some extra heat from the compression, the friction, and so on to get to this degenerate state. But yeah, it's mostly this residual temperature.
But it will cool. So over time, just like any hot thing, a mug of hot coffee, it'll cool down to its surrounding ambient temperature, which is pretty cold in space. So gradually, this really, really hot, dense thing will become a very cold, dense thing.
Yeah. So we'll park that idea.
Okay.
Because
Put that aside.
We're going to come back to that one.
Good.
But yeah. So we have our white dwarfs. So they're not really doing anything in terms of fusion. They're just sitting there being hot lumps of very, very dense star leftovers.
Cool.
Yeah.
Sounds good.
So there's kind of three things that I want to, my three favorite things. I'll tell you briefly what they all are, and then we'll look at each one individually.
We'll delve.
The first one is kind of sort of, I guess, one of the things that white dwarfs are very famous for, which is that although white dwarfs themselves don't, or the stars that make white dwarfs won't go through a supernova reaction, white dwarfs kind of buck that trend a little bit, because then they say, well, hang on, there might be another way to have a supernova, even if you're not big enough on the first try.
Right. Supernovas are for larger stars.
Yes.
Only. But the white dwarf has found, white dwarfs can find a loophole.
Yes.
A back door.
Exactly. Yeah, I like that.
Nice.
Yeah.
Okay.
So they can be tiny but mighty. So that's the first one. Second one is that actually we can argue that white dwarfs might be the most common variable stars in the universe.
Cool. If you're into variable stars, which I know you are, then having lots of those around is interesting.
Yep. And the last one is that white dwarfs will undoubtedly become the most common stars in the universe. In fact, black dwarfs will become the most common stars in the universe.
All right. We've got some stuff to unpack here.
Yeah.
So what was number one again?
Small but mighty.
Right, small but mighty. Okay, so let's delve into that.
Yeah.
White dwarfs shouldn't be able to make a big bang, but they can.
They can.
So how?
Under very certain conditions, yeah. So if you think you've missed the train on the supernova business, so stars that are larger than around about 10 solar masses, we expect will have a supernova, right? And
Larger than 10.
Yeah.
And we've been talking all this time about smaller than 10, so we've missed the cutoff.
Yeah. Exactly. But white dwarfs, as you say, have found this amazing loophole. Yeah. Now, this whole boundary condition of 10, are you bigger than 10, are you smaller than 10, exists because the size of a white dwarf has an upper limit.
Right.
You can only be around about 1.44 times the mass of the sun and still be a white dwarf.
That's quite specific.
It's very specific.
Right. And is that related to the electron degeneracy? Is that?
It is,
right.
Yeah. So the electron degeneracy pressure can hold you up, right? If you're very, very compact, very, very massive, but only to a certain point. Only up to 1.44 times the mass of the sun. If you get any bigger than that, electron degeneracy pressure can't do it. It breaks.
Right. Does it even try? Is it able to hold it up for a bit, or do we just sail right on past that limit and go, no, we're still going?
It's a really hard cutoff. It's kind of you can or you can't, and that's what happens.
So does that straight away go to the next layer of weirdness down, which is what, neutron stars? Is that what
neutron
happens?
stars, yeah. So what happens is the electrons and the protons in the sort of soup, the plasma of the star, actually come together to form neutrons, so you just end up with your ball of neutrons. Right.
I mean, there's a subatomic, or there's a particle interaction, which it's not that the proton eats the electron or anything like that, or the neutron gobbles up an electron or anything. It's that there is an interaction which says, well, electrons and protons can merge to make a neutron. That's a thing that can happen via other intermediate particles. But, you put enough pressure on there and that happens quite a lot.
Yeah.
Even though in the world around us it's reasonably rare. Put it into a neutron star and it's that's all the go. It's all the rage.
These extreme environments are fairly, well, they're not that common, but they're common enough in astrophysics. So you won't find them here on Earth, but you find them in these really, really interesting
You know what? I think that's a good thing. I don't think we want a neutron star here on Earth.
Yeah, so neutron stars, so then you've got this thing called neutron degeneracy pressure, and that's holding up the star instead of electron. Neutron degeneracy pressure is a bit stronger. It can hold up more mass.
Right.
So you might have think the ship sailed. If you're less than 10 solar masses as a star, that's it. You count supernova. Yours is your future is that you will have this puffy thing. You end up as a white dwarf. It's all very calm. Not really calm, but compared to a supernova, it's a very calm ending to your life.
And just making that link there for a second, you mentioned the 1.44 times the mass of the sun, but that's the core. That's the white dwarf bit. So that's after you've sloughed off all of your outer layers. You might have started with, up to 10 times the mass of the sun, but all the rest of that's gone. If you've got 1.44 or less left over for your core, you're a white dwarf. That's fine. Anything more than that, you're not.
Yeah.
Okay,
exactly.
so that's your cutoff.
Yeah. So, but the back door.
Yes.
Right. There's a very specific scenario where if you're a white dwarf, you can still achieve a supernova.
Excellent.
That is your goal.
Well, I mean, it should be because you want to go out with a bang, right?
Yeah. Okay. So I'm going to have two hands here, and I know this is a podcast and you can't see my hands.
So imagine Emily's hands.
Right.
Yep.
But I'm going to work with your left hand and right hand. So if you have them available, use your left hand and right hand.
Okay, everyone hold up your hands, or if you need to borrow a friend's hand, do that.
Yeah. So we have two hands, right? Two stars, a left-hand star and a right-hand star. Now, these stars were born at the same time and in a binary pair. So they're going around each other, right?
So we have a binary system. Good.
Yep, two stars. However, left-hand star is slightly bigger than right-hand star. So I'm going to make my fist very slightly bigger because otherwise I'll forget and get...
Listeners, you're missing out on a treat here. This is great.
Yeah, so that one's slightly bigger. Now, left-hand star, slightly bigger, means it goes through its life cycle slightly quicker.
Right. Bigger means faster.
Yep. So it goes all the way through, finishes using up all its hydrogen, goes through helium, does all the red gianty stuff that you can listen to in other podcasts. And then it's puffed off its outer layers and it has become really tiny white dwarf.
Okay.
Right.
All right.
Teeny tiny white dwarf.
And it can do all of that without completely destroying its binary nature with the other star. Like that's all okay. We can do that.
Yeah. Okay. So now I'm using my thumb to represent that left-hand star is now white dwarf.
Okay.
Right.
Binary system, left-hand side, white dwarf. Got it.
Okay. Now, right-hand star, slightly lower mass.
Yep.
Enters its sort of red giant and so on stages slightly
it's
later.
lagging behind and starting to puff up.
Yeah, so now that starts to puff up.
Yeah.
Now, the orbit, we won't go into the reasons, but the orbit's now such that when right-hand star puffs up so much that actually some of its outer layers are more attracted to being on white dwarf star than they are to being on, what are we left? Right-hand star. Yeah.
The white dwarf starts stealing some of its friends' stuff.
Yeah.
Just starts pulling it away.
Yeah, and starts accreting it. So white dwarf star, left-hand star, might have originally been 1.3, 1.4 even times the mass of the sun, merely just being a white dwarf. But now it's getting more mass, and it's getting more mass, and it's getting more mass, and so it gets bigger.
It can't do that forever.
It can't do it forever.
Because we just said there's a limit here.
Yeah, it gets to 1.44 times the mass of the sun.
And... boom. Right.
Yeah.
So you can have a supernova, because I've always imagined a supernova as being, you've got, a normal star, right? And it's big enough and it goes through and presumably does still puff up. But then it reaches this point where there's nothing holding it up anymore. And the supernova is where it collapses down and then it does form a neutron star, right, in the center. And that's really like rock solid. Like that's madly hard. And so all the other stuff that's collapsing down on that bounces off. Have I got that right?
Yep.
And it bounces off like really hard, like one of the biggest booms you can possibly imagine. So that's what I'm thinking. But that's not what we've got here. We've got that where it's like you haven't got the outer layers, you've just got the core bit. So
Well, you've still got lots of stuff. So you still got all the puffiness that's being thrown around by right-hand star, right? And you still have that contraction because you're going from something that's the size of a white dwarf, which is maybe the size of the Earth, to something that's the size of, I don't know, a few kilometers across.
It's like the size of a city,
Yeah.
right? Yeah.
So it just goes, and that happens very, very quickly. It's this almost instantaneous contraction, boof, right? Because you've just crushed this thing down to the neutron degeneracy pressure limit.
So even if there isn't, the rest of the star around it, there's enough for it to go, well, we're still going to have an explosion anyway.
Yes, exactly. And
Awesome.
the whole process of changing your protons and electrons into neutrons, all that kind of particle physics is still all happening.
Wow. Okay. So it manages to find the back door, we're going to change from white dwarf to neutron star. We're going to have an explosion. How's the partner at this point? How's it getting on?
Oh, yeah, it's screwed. You're not going to be that close to a supernova and be happy about it.
So that's a bit rude, to be honest. Like, I'm going to steal some of your stuff. Like, you're just trying to do your stellar evolution thing. You're trying to do the thing that you've just watched me do and think that was fun. I'm going to become a white dwarf too. But no, I'm going to rudely interrupt you and actually blow you away.
Yeah.
Thanks very much. This is rude.
Wow, the personalities of white dwarfs that you didn't know you didn't know.
It's sibling rivalry at its worst. It's terrible.
So these are some of the biggest explosions. Well, they are the biggest and brightest explosions that we have in the galaxy, supernovas. And the most amazing thing about these things, I mean, you can quote every stat you like about how bright these things are. They're insane, right? But there's still only about 1% of the energy is even coming through to us in the brightness. So
in what sense? Like, where's the rest of it?
The energy of the supernova, only about 1% goes into this insanely bright, massive explosion-y thing that we see.
Right. Where does the rest of it go?
Oh, neutrinos.
Oh, right. Okay. Again, don't stand too close to a supernova because, I mean, neutrinos will happily pass through you, but standing too close to a supernova, you could get killed just by the neutrinos.
Yes.
Like, that's madness.
It's madness.
That's absolute insanity.
Neutrinos are wonderful. So, yeah. So I like this. I like this back door. I like this terminology and I like this whole process that if you didn't really fancy that you were going to end your life as a white dwarf, if you've got a binary companion.
We have a way.
Yeah.
We have a way. Does that kind of supernova have a special name? Is that a particular kind of supernova?
They are. They're type 1A supernovae.
Right. Okay.
Yeah.
As opposed to
type 2s, which are these stars just merrily, more than 10 solar mass
they're big stars that are just doing what
exploding.
they do.
Yeah.
Right. Okay. Yeah. Type 1A, does that mean that there's a type 1B? Are there?
Yeah, there are some subclasses. They're to do with kind of exactly what the type of spectra. So how many, what the hydrogen lines are like,
Okay, let's not get too hung up on it.
Yeah.
Point is, those are type 1A supernovae. Okay, cool.
Yeah. And the brilliant thing about them is they are some of the most useful tools that we have in astrophysics for measuring distance, because although, a star can explode and you don't know what its mass was, right, when it explodes.
Like a type 2 supernova.
Yeah.
Right, it could have been anything.
Could have been anything.
Yeah.
Could have been 10, could have been 20, could have been 50, who knows, right? And therefore, you don't know how bright that star is, right? It could be really bright and quite far away, or it could be quite dim and quite close.
Right, and you don't know.
You don't know.
You don't know.
So
because those things will look the same.
They're just hard, So they're hard to think. Whereas these type 1As, we know exactly how much mass exploded.
Of course.
Every single time.
Because it was less than 1.44, and then it got to 1.44, and at that mass. Does that number have a name?
It's the Chandrasekhar.
That is the Chandrasekhar limit.
Yeah.
At that limit is when it happens.
Mm-hmm.
It doesn't sort of reach 1.44 and carry on to 2. It's
Nope.
like, no, 1.44, that's it. We're done now.
Yep.
End of conversation. Boom. And so you know how big that was.
Yes. And so you know exactly how bright that was.
Which means when you see it, you now know how far away it is.
Exactly.
It's so clever.
It's so good.
So clever. Thank you, physics.
Yeah, and this is how we discovered dark energy, for example.
Right. Yes, it was using that kind of supernova to measure distances.
Yep.
And so remind me what the logic here was. How did we get from that to dark energy?
So we measured the distances of different galaxies, really, really distant galaxies, and we're able to say from those distances exactly how fast those galaxies were traveling away from us. And we were able to then measure the fact that the universe is not only expanding, but the rate of expansion is accelerating.
Right. And that's
So
the
we're getting
weird
faster.
part. That's the weird part. Because when they did the research, they were wanting to do all of that right up until that last bit, right? We can use these supernovae, these type 1a supernovae, these white dwarfs using their loophole to measure distances. Like that was the whole point. And that means that we can measure the expansion of the universe and the rate of expansion of the universe going out really long distances. And so from that, we can figure out what's happening in the universe. And what they actually found out was, weirdly, the further away you get, the faster that expansion seems to be. In other words, the universe seems to be speeding up.
Yep.
The expansion is speeding up, which is like, what the hell is that? Where does that come from?
Yeah,
It
someone's
should be
got their
slowing
foot
down.
on the gas,
Should be
basically.
slowing down because gravity is pulling in, right?
Yeah, yeah.
And so that's where the notion of dark energy came from, which is, well, there's something. What's the something? We don't know. There's just something which is pushing everything apart, and huge mystery still. But that's how we found that,
Yeah.
which is
So
awesome.
probably the biggest, you could argue, mystery that we have in astrophysics.
Amongst many, but yeah, that's a big one.
It's pretty big. Dark energy, you can rewind back to saying, well, that all comes about because of supernova, which if you rewind that back, that's all because of white dwarfs.
Yes. Well done, white dwarfs.
Yeah.
Excellent. So that's number one. That's
Yeah.
just one
That's
of,
just
of
one of
Emily's top three.
Yeah.
Excellent.
So my second one,
Mm-hmm.
now this is, I'm not going to lie, this is going out on a limb a little bit here.
Okay.
I'm taking an idea and I'm running with it.
You're taking liberties.
I am. But I'm going to make the claim that white dwarfs are the most common variable stars in the universe.
Okay. So variable stars. Let's pull this apart a little bit. Variable stars.
Yep.
Remind us what you mean when you say variable stars.
It's a massive catch-all. But anyway, so variable stars are stars that vary in brightness. Of course, the ones that I am interested in research-wise are stars that pulsate. So they have some kind of oscillations, which means that their brightness varies because their surfaces are varying.
Right. I mean, all stars vary in brightness to some degree. I know that the sun is sort of, belching out great plumes of stuff every once in a while. But you're talking about things which are a lot more interesting than that. And so why, give us a for instance, why would a variable star be doing something that's interesting? What's going on?
Yeah, so they can set up different pulsations which are driven by some sort of changes that are happening in the interior. So you get these periods which are very long lasting. So the most famous ones of these are Cepheids. Cepheids have a setup in their interior where they get a bit hotter, they expand. The expansion means that they get a bit cooler, so they cool down, so they contract, but then they get a bit hotter, and so they expand.
And repeat.
Yeah,
Yes.
exactly.
Right.
And the whole radius of the star gets bigger and smaller and bigger and smaller and bigger and smaller.
Right. So it's just oscillating away.
Yeah.
Like that.
Yeah.
Cool.
So then there's lots of different types of variable stars, lots of different pulsation mechanisms. If I started to tell you about all of them, this podcast would be really long.
But I can see why you're interested.
But white dwarfs do have pulsations.
Right.
And they are actually really, really interesting because these are lumps of degenerate material.
Like Earth-sized.
Yeah.
Yeah.
And
like
these-
that's really small.
They're really small, and degenerate material is also very weird.
Right.
Like, let's not pretend that the physics of degenerate material isn't odd, because it is. It's really odd.
This is not normal material.
No, it's not normal star stuff, right?
No.
So the fact that they have pulsations at all is quite interesting. And it seems that the pulsations are actually more linked to not so much the carbon and oxygen that most white dwarfs are made of, which is the degenerate stuff, but sort of layers of hydrogen or helium in their atmospheres, so kind of the outer bits of them. So they do still hold on to a bit of hydrogen and
Right.
helium. They're
It's not as clear cut as these are only made out of carbon and oxygen. There's a lot of that, but there's some funky stuff around the outside.
Yeah. So they do have these atmospheres which can then drive pulsations in them,
Right.
depending on exactly what they are. So there's lots of different types of white dwarfs. I'm not going to be exhaustive and talk about all of them. But the one I want to particularly highlight are called DAV.
DAV. Go on then.
or also known as ZZ Ceti
Okay.
variables.
Right.
So ZZ Ceti, because there's a practice in pulsations and variable stars to name a class after the first one that you find.
Okay.
It's not even defined practice. It was kind of like, oh, that star looks a little bit like that other one that we saw. Oh, that one looks like that one again. And so you kind of just call them all by the original.
Yeah. Okay. Fair enough.
But I guess another way to call them, so that's why they're called ZZ Ceti. ZZ Ceti is an example of these. But they're also called DAV because DA is a type of white dwarf and the V stands for variable.
Okay. So this is quite arcane astronomical nomenclature here.
But it's really important.
Yes,
So
no, I'm
you
sure it
needed
is.
to know that.
I mean, look, jargon is important because you need language, but it's not something that we can easily explain to the listener. Just take it for granted, people, that these names are meaningful to people who work in this area. Carry on.
You're right, DAV white dwarfs. So now most stars will end up kind of here. So if you imagine you've got your white dwarf that's just kind of been emerged from its murky cloud of the atmosphere of its previous host star. No, previous star. That's kind of the white.
Previous incarnation.
Yeah.
Yes.
So that will just slowly cool, right, over time. So the DAVs have cooled down so that they're kind of around between 12,500 and 11,100 Kelvin. So that's actually quite a big cooling for a white dwarf.
Okay.
Because they start off in the
tens of thousands.
hundreds of thousands to millions. Well, at least the cores of the stars were. I can't call them host stars as if there's some sort of parasitic thing. They're not. So they're cool. And the way that they cool means that they do pass through this kind of region of instability in temperature, effectively. So once you hit this temperature, if you've got a bit of hydrogen surface, which these DAVs kind of do, then that can start to pulsate and give these oscillations, which are on the order of kind of a few minutes up to maybe half an hour.
Right.
In time.
Do we know? So, do we know why they're pulsating? I mean, what's the mechanism?
Yeah. So, what happens is with all pulsations are driven by the fact that you've got energy trying to get out of a star, and you've got something that's blocking that. So, and the thing that blocks the energy getting out is different for each different class of variable. But in this case, it's to do with the structure of hydrogen. That means that hydrogen ends up blocking a little bit, so you end up with these standing waves set up within the hydrogen layer, effectively.
Right.
So the star's not getting bigger and smaller. It can't do that. It's degenerate anyway, right? But the layer of the hydrogen kind of has almost these like wiggly wobbly waves going around, so they're horizontal rather than towards us and away from us.
Right. I can see that. I mean, the analogy with, the strings on a guitar or the surface of a drum, right? To set up different vibrations on those, you add energy. And if you add energy in different ways, you get different kinds of vibrations. And so, yeah, I can see that. The thing that I find kind of surprising is like they're really small, right? And so it's not easy to see, although I guess you said they are very bright. And so they're easy to see in that sense, but maybe we can come back to that.
Yeah.
But they're really small. And one thing that I do know about vibrations is that the speed of the vibration is related to how big the thing is, right? And so if you've got a really big star, a vibration has to travel across the entire breadth and width and length and height of that star in order to actually do anything. This is tiny. And so you've got tiny little wiggles. I'm amazed we can see that, is my point.
Well, they're quite new in that sense. I mean, it's only been recently that we've been able to really well observe these types of stars. And let's be honest, there's not a lot of them. I didn't find an exhaustive list, but there's around about maybe 100 to 150 of these things that we've observed.
Okay. But you started this. This is number 2. You started this by saying, yeah, but most common kind of variable star. So how do you square that circle? We've only seen a few of these, relatively small number of these, but you're making a bold claim here.
I am making a bold claim. So let's come back to that visibility thing. Yes, they're very, very bright because they're very, very hot, right? 11,000, 12,000 Kelvin, that's still hot on anyone's scale. Right?
Okay.
But they're tiny. And so the brightness of an object is not just how hot it is, but it's how big it is. And those two things change the visibility, right? So they are really, really faint, not because they're not hot, but because they are tiny.
Right. Okay.
So, yeah, planet-sized, right, objects. So that means that they are really hard to find. But we do know that most stars will end up here. So we estimate that maybe somewhere around about 6 to 7% of all stars in the Milky Way are actually white dwarfs.
Right now.
Right now.
Wow.
Despite the fact we only know of a couple of hundred in total.
That's quite a lot.
Yeah. Yeah. So, I mean, we've got, 300, 400 billion stars? Yeah.
So we're talking billions of them just now.
Yeah, exactly. So there's loads of them. We just can't see them because they're so faint. Even if they're close, they're so faint. They're just so hard to spot. So, and then if you take that's the whole white dwarf population, we reckon maybe 20 to 25%, maybe up to a quarter of all of those stars are these DAVs stars.
These variable ones.
Yeah.
So you're still talking like billions.
Yeah.
Wow.
So even though we might know of quite a lot of Cepheid variables, for example, we know loads of red giants stars that are pulsating now, thanks to space telescopes. But these white dwarfs, you're coming from a population of many, many, many. So even though we only know about a few, there could be really, really billions of them.
So that's interesting. Does that, like, can we do anything with that? Like, is it likely that we're going to be able to see more of these with telescopes and technology coming online? Or is this a bit of a moot point that we reckon you're making the claim, you're staking this claim, which is these are the most common, but we'll never see any of them?
Well, we've got a few, and we are getting more and more. So when I say about 150, I think there were about kind of maybe 70 odd that we knew about before we had space telescopes like Kepler. Kepler added, I don't know, between 50, around about that ballpark kind of number. And that was a telescope that just stared into very, very deep kind of parts of the galaxy for a long, long period of time. So those kinds of missions are going to be the ones that we're going to pull out more of these things with.
Right.
So yes, there is a definite, like Plato's an upcoming mission that will be really, really useful for this kind of work. Other missions that do sort of really long stares, because then you can start to build up really good images of really faint objects.
Yeah, I mean, you have to look for a really long time in order to see something that's really, really dim. Yeah, okay.
Yeah. So yes, we will find more. And they are really useful because they do contain a lot of information that you can then backtrack to push back into how did the star even start out its whole life cycle? Everything you can trace backwards, right? You can figure out how when you look at the pulsations, you can actually see them change their period over time as the star starts cooling. So as it cools, it changes its pulsation period. And by measuring that, you can see things like the age of the white dwarf. So you can actually see how old it is. You can see things like the mass. So and that mass is then all linked back to what was the mass of the core of its original star. Like all these really important things that you wouldn't necessarily get out of just observing stars in the main part of their life.
So by studying the variability, what you're saying is you can work backwards and figure out a heck of a lot about the white dwarf as it is now or as it was, but also even further back to where that came from, the original star.
Yeah, and these are getting to some of the coolest white dwarfs that we can observe, which is interesting because when you start getting down to these cool ones, you're starting to put limits on the age of the universe.
Wow.
Because these cool stars are getting down to a few, like sometimes billions of years old, right? Sometimes tens of billions of years old.
Well, we haven't got tens of billions. I mean, we've only got...
Well, exactly.
We've only got 10 and a bit.
8, 9, 10 billion years old objects. So with that age measurement, you can start to say, well, the universe can't be... It has to be at least that old
for
these things to exist. But if it was a huge amount older than that, then we would see older white dwarfs, right?
So, yeah, that allows you to sort of start playing around with those boundaries on, well, how long can things have been around? You know, what are the oldest things?
Yeah.
And if you can measure different kinds of old things, that puts different boundaries on how old things are.
Yeah. And that's true for the galaxy as well. You can say, well, what's the age of the galaxy based on that? So it's really, really useful stuff.
Yeah. Nice. Cool. So that's number 2.
Yeah.
Number 2. A bold claim, but I like where you're going there. So number 3. What was number 3?
Number 3 is that these will definitely become the most common stars in the universe.
All right. Take us on this journey.
Okay, so we've already come down to the idea that white dwarfs, they start off with some temperature and then they just cool and they cool and they cool and they cool. And these DOVs, we're talking about ones that have cooled down to 10,000, 11,000 Kelvin. And they're a few, maybe 10 billion years old, something like that. But let's just run the clock forward.
Okay.
What happens? They keep cooling, they keep cooling, they keep cooling. Just like your coffee cup, right? It eventually cools until it becomes the same temperature as the room that you're in. White dwarfs will eventually cool to the same temperature as the universe.
As space.
The background, yeah. So these are what we call, they're theoretical objects, but we call them black dwarfs.
Right. Because they're not shining anymore. They've
No.
run out of energy.
No, if you're the same temperature as the surroundings, then your temperature and therefore light output is equivalent to your surroundings,
Yeah.
right?
And you can't see that.
Yeah.
It just blends in. It's
Yeah,
the
it's
perfect
just black.
camouflage.
Everything
Black
fades
against
to black.
Yeah.
Yeah, exactly. So black dwarfs, I say they're theoretical because, well, we haven't got any because quite simply.
How would you see one?
But also quite simply the universe isn't old enough yet. Right? So our best estimates is that they definitely will take longer than the current age of the universe to cool to the background temperature.
So we wouldn't expect there would be any out there yet.
No, they're not there yet. I think the oldest ones we have are around about 12 billion years old.
Right. The oldest white dwarfs
Yeah.
that we found. Okay.
Yeah.
Okay.
So, yeah, and they're still a few thousand degrees.
Right. So over what kind of timescale would we expect it to become dark then? And is there a cutoff? Like, at what point do you say that's no longer white dwarf, that's grey dwarf or black dwarf, or like, do we care? Is that important?
No, I
an
think
important distinction?
These are really interesting because we estimate, based on just the cooling tracks and the cooling physics, that it would take around 10 to the 15, so that's 1,000 billion years, for a white dwarf to cool to 5 Kelvin.
Hang on, isn't that a million billion? A billion 10 to the 9, 10 to the 15.
Oh, 6, yeah. So a million billion, yeah. So a million billion years. Yeah, you're right.
Yeah.
So a lot even longer still. So that would take about 1 million billion years to cool down to 5 Kelvin.
Right.
So this is 5 Kelvin. It's 5 degrees above absolute zero,
Right.
which is minus 273.
The cold
Yeah.
of the depths of space.
Yeah.
Yeah.
Yeah. So that's still 5 Kelvin above that. So yeah, that's a really long time just to get to that temperature.
Mm-hmm.
Should we call that temperature a black dwarf?
I'd be happy with that because that's
Yeah.
still really cold.
Because cooling below that level, and there's a reason why it's 5 Kelvin, cooling below that gets really complicated.
Does it? Why?
Well, because you need to start taking physics into account that we don't really understand.
Physics. It's always getting in the way. So what's the problem there though? Like we have stuff colder than 5 Kelvin in the laboratory all the time. It sounds really cold, but we do it.
But not so much in the universe, out in the wild, if you like.
Right.
Because there are things like, how does dark matter behave at those kinds of temperatures? Well, that would be a question we could maybe start to answer if we understood what dark matter
If we
was.
actually knew what it was.
Yeah.
Yeah.
So there's some open questions there. We're talking now on timescales where proton decay could become important. So the idea that the proton and the nucleus, this is an open question. Do protons ever decay?
Right. And this is not protons inside a nucleus. This is just looking at a proton by itself floating around.
Yeah.
Is it forever stable or not? And we don't know.
No. If it does decay, it's on these orders of, billions of hundreds of millions of billions of years, right?
Yeah.
It's really long timescales.
Yeah.
It's
I
longer
mean, it's nothing to worry about. People,
No.
if you're listening to this going, oh my God, are all my protons in trouble? No, you're fine.
No.
It's more of a esoteric physics question, an important one for physics, but nothing to get really worried about. But it has long-term impact.
It does, and especially if you're talking about these millions of billions of years, right? It's important then to know, do protons decay or not, because that will affect whether or not there's some kind of evanescent temperature that's coming through in your white dwarfs that keeps them just that little bit warm.
Right, because
Just
if
that
the
little bit of a
protons
background.
are decaying over very long time periods, they're not all going to go at once.
No.
One will go over here, one will go over here, but that'll put out some energy. I mean, they will decay to go from a higher energy state to a lower energy state. And so that'll spit out some energy in some form, which will just keep burning away and adding tiny increments of energy out there into the stuff of the universe to just keep things, at a few degrees.
Yeah.
Maybe.
So the physics is weird. Let's summarize. Below 5 Kelvin. If we can say, I would say 5 Kelvin seems like a.
All right. Well, let's put that cutoff in there. We are going to
You're a black dwarf.
unilaterally decide that's where we're drawing a line, and physicists can worry about the rest. It's still pretty cold.
It's very cold.
Yeah.
Yeah. So all you got to do now is wait.
Right.
Because everything in the universe will eventually end up in a star, right, at some point. And as we know, 97% of stars are going to end up in white dwarfs. And they're just going to cool. And that matter is locked, right? It's in that white dwarf. It can't be reused under very normal circumstances. I mean, you could contrive very rare scenarios where white dwarfs might merge and things like that. But in a broad sense.
Yeah. I mean, unless the universe all sort of collapses down upon itself again, like these things are really spread out.
Yeah.
the chances of them, I mean, I guess over an infinite time frame, they're all eventually going to collide. But, no. Eventually you're just going to have a very dark space filled with very dark things.
Yeah. So, and the universe is expanding, right? And its acceleration is expanding. So these things are going to be just blobs that are cooling and they're going to become further and further and further and further apart.
That feels a bit sad.
Everything's
really.
going to end up in black dwarfs.
Wow. I don't know how I feel about that. I mean, fortunately, it's far enough away in the future that I don't really have to have an existential crisis about it. But, yeah.
So I think those three things together means that white dwarfs are actually, they're not the poorer cousins of the neutron stars, as you might suspect from, a quick peruse of stellar evolution.
Well, neutron stars get, they get all the press. They get all of the excitement, right? But what you're saying is white dwarfs, they're eventually going to rule the universe.
Absolutely.
Well, Sophia, I hope that has given you enough material for whatever it is that you're ultimately going to do with your white dwarf project. And please let us know. Like, I'd really like to know what it is that you're planning on doing with this. But I hope in some way the Syzygy podcast has been able to give you some inspiration, some fodder for your creativity. This has been a fun one, Emily.
Absolutely.
I like it. It took me to places I wasn't expecting to go. I'm probably going to lie awake tonight just staring up into the dark of the room thinking about a distant future of black dwarves.
Well, you could think about Whiskers on Kittens if that helps instead.
Okay, maybe I'll do that. Listen, if people like Sophia wanted to get in touch with us and suggest another episode for the podcast, how could they do that? How did Sophia do it in the first place?
Well, we've got this wonderful, wonderful website that has a link and a click and a box that you can put your words into, and then those magically turn into an email that arrives in your inbox that you send to me saying, hey, this is cool, let's do this. And I just say yes. By the mysteries of the internet. And does that website have a URL? Does it have an address? I suppose it does. Yeah. It's syzygy.fm, syzygy.fm.
Yes, go there. You can find all of our episodes going all the way back to episode dot, and all the info and all the pretty pickies and all of that. It's a cool place to be. It's also got a big page of thank yous to all of the people who support us on patreon.com. You can become one of those. Head over to patreon.com/syzygypod and you can throw us some money to help us keep the electrons flowing through the website and to do the things that we do. But you know what? The best thing that you can do to support the show is just to spread the word around. Tell people in your life there's this fabulous show. It's called Syzygy, and you will find out about ultimately how the universe is going to be populated with dark black dwarf stars and blow people's little minds. That's the best way to help the show, and that's what we do this for, is to spread the love of astronomy throughout the universe. Look, we're going to have to go now. That's the end of this episode, so we will see you in an undefined period of time as we're learning here on the show. It could be a week. That'd be nice. It might be a fortnight. It might be longer. We'll just have to see how we go. But Emily, I'll see you next time.
See you later.
Bye, everybody.